In this video, what I would like to show is, outside the technicalities, just a general kind of idea about why we want the integrating factor to look like we do when we're solving a first-order linear differential equation. So let me just show you, remind you what a first-order linear differential equation looks like. In standard form, we have y prime plus p of x times y is equal to q of x. We won't get into really discussing what p of x and q of x are, but this is just a standard form of a first-order linear differential equation. Now, in what's coming, what we will need is a little fact that I'll share with you right now, and that is if I have some function, say f of x, and I take the logarithm, of course, f of x has to be greater than 0, etc., etc., etc. But outside of these technicalities, imagine that I have some function of x and I put it inside the logarithm, and then I want to take its derivative. Again, assuming that f of x is differentiable at x and ln is differentiable at f of x, what we then can do is we can use the chain rule, obviously, and this just becomes 1 over f of x times the derivative f prime of x. So I'm just going to keep this in a little box, just so that we keep it for later. And the idea of the method of the integrating factor is that we want the left-hand side of our differential equation to look like this: the derivative of some function times y. And the reason we want the left-hand side of our differential equation to look like this is if the entire left-hand side is a derivative of something, we can integrate both sides with respect to x, and that will give us y here on the left-hand side, and hopefully we can isolate for y. So if we want the left-hand side to look like this, the question then becomes, what should I choose f of x to make the differential equation that I've been given? What should I choose f of x to be in order to make it look like this? And to start that investigation, what we're going to do is we're just going to expand out what this left-hand side would actually look like. So just using the product rule here, we have the derivative is f of x times y prime plus f prime of x times y. That's just the product rule. So straight away we can kind of see that we want the left-hand side to look like this with these f of x's and f prime of x's, but the left-hand side of our differential equation that we're given actually looks like this with just a y prime. So the first thing we're going to want to do is to try to make our differential equation kind of fit this form. We're going to multiply everything through by our unknown function f of x. So just multiplying our differential equation by f of x, we get f of x y prime plus f of x p of x y is equal to f of x times q of x. Okay, so now we've got the left-hand side to look a little bit more like the way we want. We have an f of x times a y prime. That's exactly what we want. But if we look at the second term, what we see here on our differential equation is an f of x times p of x. And if we look at the way we want it to look, we want it to just be f prime of x. What this tells us is that f prime of x should be equal to f of x times p of x, which means we can rearrange this to look like p of x has got to be equal to f prime of x divided by f of x, which we know from the little fact that we started with here. If I have something that is if I have f prime of x divided by f of x for some function, what that actually really is, in secret, is the derivative of the logarithm of f of x. So this is actually equal to the derivative of the logarithm of this unknown function that we still have to figure out what it is. Okay, so now we have a relationship between the p of x, which comes from our actual question, and this unknown function f of x that we need. Namely, that if we take the derivative of ln of f of x, we get p of x, which means if we anti-differentiate p of x, that will actually end up being the logarithm of f of x. And now we're kind of in a position now to figure out what this f of x is. Finally, if we just exponentiate both sides, we get the exponential of p of x dx is equal to f of x. So this unknown function that we needed to multiply our entire differential equation by ends up being the indefinite integral, or the antiderivative of p of x, stuck inside this this natural exponential here. And of course, this is usually given the term the integrating factor. So again, outside of the details about differentiability and kind of restrictions on what these functions have to be, we can kind of see here how the form of the integrating factor, where the form of the integrating factor comes from. And it just comes from wanting the left-hand side to kind of fit this form.